Welcome back. We are going to finish up this gas laws lab that we've been working on. You did in lab. You watched the lab done by Mr. Proetta, and now it's time for you to do the calculations. So I gathered ahead of this, the information that you'll need to have gathered from watching the video, which is the metal used, which I used calcium, the barometric pressure, that's the pressure total, okay, it's going to be our pressure total, the room temperature in degrees Celsius, and therefore in degrees Kelvin, forgot my other zero there, the vapor pressure of water, and this is torr, the density of water, which I forgot to put a line in for at this particular temperature, and the molar mass of the metal used. Now, a weighing cup was massed, and then metal added to it, some calcium added to it, and when I subtract these two, I find that I had 1.1766 grams of calcium. And we're going to figure out how to get the moles of calcium in just a minute. All I'm doing is going through and doing the stuff that I don't need to do anything special for. So coming down here to look at the water that came out of the Florence flask in the tube, I had 215.05 grams of water and beaker. I had massed the beaker ahead of time, so that was just 96.52. So when I subtract these, I get 118.53 grams of water. Now, I'm going to be figuring this out as well as this, the volume of the gas that was evolved, because remember, this mass, this displaced water, was 1-to-1 with the gas, 1-to-1 molar ratio with the gas. So we can figure out, so that was the first part. The second part, of course, was determining the leftover, the remaining or unreacted HCl in the reaction flask. Okay, so first, in order to do that, we have to find the total moles of HCl. And we used a 25 milliliter volumetric pipette, and this was the molarity of my HCl. So when I converted this to liters and multiplied this, remember, molar is moles per liter, I found that I had 0.02933 moles of HCl total. So this was the total moles of HCl that I started with. Now, after I did the reaction, we titrated the remaining HCl that was in that flask, the amount of HCl that did not react with the acid. So to do that, we titrated it with NaOH. And that was simple. We ended up using 25.50 milliliters of NaOH to titrate the remaining HCl. So combining that volume in liters with the molarity we had for NaOH, we can find the moles of unreacted HCl that were remaining in the flask. So just molarity, again, that's moles per liter times the volume of the titrant in liters, and we got 0.02507 moles of remaining HCl. Now we can do one more thing on this paper before we have to go to our calculation sheet. We can find the moles that had reacted of HCl very simply. This is moles total, which we'll find in a second, minus the moles unreacted. And let's see. So the moles unreacted is right here. The moles total is right up here. So subtracting those two, we find the moles that were reacted was 0.00876 moles of HCl that actually reacted. Okay, so those reacted, those were part of our experiment. All right, now that we have all that data, we're going to be determining a few things. We're going to be determining, first of all, the volume of gas evolved from the mass, and therefore the number of moles of gas evolved from the volume. We will also be determining the ratio of the number of moles of acid to the number of moles of metal, and also the number of moles of gas to the number of moles of metal. And we have to be sure we're watching our significant figures. Okay, so having that sheet in front of you, you actually should probably be doing your work right alongside of me at the same time. First, we're going to calculate the number of moles of metal, so that's calcium in my particular case, that were used as a reactant. So we had 0.1766 grams of calcium, and calcium's molar mass is 40.08 grams per mole, so using dimensional analysis, 1 mole over 40.08 grams of calcium. And that gave us, for the moles of calcium, 4.406 times 10 to the negative third moles of calcium. We're going to continue on working with the mass of the water to find the volume of the gas. Okay, so the mass of the water, we're going to convert to volume of, of water, which is 1-to-1 ratio with the volume of H2, of hydrogen gas. So let's go ahead and do this. We found we had 118.53 grams of water. And for that particular day at that particular temperature, our density of water was 0.9978 grams per milliliter. So 1 milliliter over 0.9978 grams. And that gave us 0.8 milliliters. Now we needed this in liters, right? Because we're going to plug it into the ideal gas law. So remember, we have 1,000 milliliters per liter, and we're going to find that this is 0.1188 liters of hydrogen gas. Moving along, we're going to be looking for the number of moles of gas. And so we're going to rearrange the ideal gas equation to give us N equals PV over RT. And I typed in R incorrectly. There we go. That's better. Now, we've got our volume, we've got our temperature, and we think we have our pressure, barometric pressure, right? But remember, this gas was collected over water. We have a vapor pressure of water that we're going to have to get rid of. So if we have our total pressure, remember P total is the sum of the partial pressures, and the partial pressures here are the partial pressure due to hydrogen gas, and that's the one we want, plus the vapor pressure of water. So when we solve for the pressure of hydrogen gas, it ends up being, there we go, the total pressure, which is the barometric pressure, minus the vapor pressure of water. So let's go ahead and plug these in. Let's see, our barometric pressure was 752.33 torr. And I went and looked up on the chart down front, and our vapor pressure for water at that temperature is 19.83 torr. So our total pressure that's just due to hydrogen gas is 732.50 torr. So if we converted this, as we need to atmospheres, we'd have 732.50 torr times 1 atmosphere per 760 torr. And that has enough significant figures to not change ours. And this ends up being 0.9638 atmospheres. Okay, so now let's see what we've got. We've got pressure. We've got, from somewhere back up here, volume. We've got our temperature is equal to 295.20 Kelvin. So we've got our temperature, and of course we know R. So let's go ahead and plug everything into our rearranged ideal gas law. So N equals 4.726 times 10 to the minus third moles of hydrogen gas. Excellent. Making headway. Now, the number of moles of hydrochloric acid used as a reactant. Well, this is the total moles of HCl. Okay? And what we're going to be looking for is the moles of HCl that were reacted. So in order to do that, I'm going to have to determine the moles that were unreacted. And of course, the difference between the total and the unreacted is the reacted, and this is what we're shooting for. But in order to do that, of course, we have to find first the total moles and then the moles of unreacted. So here we're doing the total moles. And that is our volume that we used, and this was the same for all your runs, at 25 milliliter volumetric pipette, times the molarity. This was standardized, and you're, remember, going to use the molarity that was used in your lab. So this comes out to be 0.02933 moles, and this is your total. Right here, this guy. I guess what we have to do is find the moles that didn't react, the ones that were left over. Now, how did we find that? Well, we found that by, here was our flask, and you had reacted all the calcium or whatever you reacted with the HCl that was required. And so in here, there were little leftover HCl molecules, right? So what you did then was titrate that. Okay? You titrated with standardized base. Until you reached the end point. And at that point, you knew the volume of the standardized base and the concentration of that base. Okay, so what good did that do us? Well, let's take a look at the stoichiometric reaction that we did. Remember, we're shooting for the number of moles of unreacted hydrochloric. And that is going to react with our NaOH that we're putting in from the burette. Remember, when this becomes a pale pink, at that point, our moles of acid equal moles of base. Now, since both NaOH and HCl are monoprotic, we end up with a perfect 1-to-1 ratio, which is wonderful. Now we know the moles of NaOH that were needed. And since we had 1 mole of HCl for every 1 mole of NaOH, we found the moles of HCl that were unreacted. Okay? A molarity of 0. And this was standardized, remember, 8067 mole NaOH per liter. And when we did the titration, we found that we used 25.50 milliliters or 0.02550 liters. This left us with 0.02057 moles of NaOH that were required to titrate the unreacted HCl. So let's make that conversion. 0.02057 moles of NaOH times that molar ratio, 1 mole of HCl per 1 mole of NaOH equals 0.02057 moles of HCl that were unreacted. So now we're simply going to find the number of moles that reacted. So remember, we said moles total minus moles unreacted equal moles reacted. So let's fill that in. From step 4, we had 0.2933 moles total. And from the step we just did, 0.02057 moles unreacted. And that left us with 0.00876 moles of reacted, because that's what we care about, HCl. Okay, all we've got left to do now is our ratios. So the first one we're going to do is the number of moles of HCl that reacted to the number of moles of the metal that reacted. So we need to go back to the first page, and we're going to find our moles of calcium. Okay, so first of all, that moles of unreacted HCl right there, and that was 0.00876 moles. And the moles of calcium that we found on the first page was 0.004406. And when we do this math, we find that we had a ratio of 1.99, 3 sig figs here, moles of HCl to moles of calcium. Well, that's good. That's a good start. Now we're going to do the last ratio, which is the number of moles of gas to the number of moles of metal. So we've got to go back to the last page again, and we found the moles of H2 were 4.726 times 10 to the minus third. And we found from up here that the moles, or also the last page, that the moles of calcium were 4.406 times 10 to the minus third. So let's go ahead. Ratio 1.073 moles of hydrogen gas per mole of calcium. Finally, based on the calculated mole ratios, write an equation. So our equation is going to be calcium. And what we did for both of these, step 7 and step 8, was saying that we had 1.99 moles of HCl per 1 mole of calcium, and then 1.073 moles of gas per 1 mole of calcium. So we have to have 1 here. And of course, we don't write that. Plus, now the next thing we're going to do is figure out the moles of HCl, and we had 1.99. Right here we had 1.073 moles of hydrogen gas per 1 mole of calcium. And this was our total reaction, which is pretty close. So let's finish filling out our sheet with all the stuff that we have just gotten. So now we've filled in all of the numbers that we calculated in the last few minutes. All these that I put in red. And the only thing we have left to do is our post-lab quiz. So here we want to use a comparable range of weights for strontium, if I chose to use strontium in this experiment. And what I need to do here is first figure out the range of moles. So we're using grams times the mole over grams from the molar mass. So 0.1 divided by 24.31 gave us 4.114 times 10 to the minus third. The other end of that range was 5.060 times 10 to the minus third. Okay, so let's check for calcium. At the low end of the range, 0.1648 grams over 40.08 grams per mole gave us 4.112 times 10 to the negative third. And the 0.2, the upper end of the range, gave us 4.990 times 10 to the minus third. Now, if we look at these things, both of them have a lower end of their range, which is very close to 4.1. And both of them have an upper end of their range that's very close to 5.0 times 10 to the minus third. So that's what we're going to say. We're going to say that if magnesium used that much, if calcium used the same amount, then strontium, which is also an alkaline earth metal, is going to be 4.11 to 5.0, as well. About 4.1 to 5.0 as well. So now we just need to multiply our 4.1 times 10 to the minus third to 5.0 times 10 to the minus third. Now we looked up our strontium mass and put it in there. So now all we have to do is multiply 4.1 times 10 to the minus third moles times 87.62 grams and figure out what we have for the lower end of our range. And that is 0.3601. Going to do it with the upper end of our range. It's 0.4381. So that's what we do with this. And of course, you're going to have to do all the calculations out to make sure I'm right for your quiz.